Multivariable Calculus, Section 12.8, Directional Derivatives and the Gradient. Now the gradient is going to be studied some more when we get to Chapter 14 on vector fields, so it's très importante. Alright, so according to Wikipedia, what is the gradient? In mathematics, the gradient is a generalization of the usual concept of derivative to the functions of several variables. If f of n variables is a differentiable function of n variables, its gradient is the vector whose components are the n partial derivatives of f. It is thus a vector-valued function. Okay, so here's a surface which can be described by this function, and I'm not going to actually compute the partial derivatives here because, as you can see, they'd be a bit messy, but let me just give you the idea here. The gradient then is, the first component is the partial derivative with respect to x, and the second component is the partial derivative with respect to y, and so we get a two-dimensional vector. Now you can see in the picture that these vectors have been projected onto the xy plane, but in actuality you could move them up, straight upwards to a point on the surface, and then they would point out from the surface. Okay, so let's say we have a point and we'll call it A, B, and C on the surface. Then the gradient evaluated at that point would be the partial derivative with respect to x evaluated at the point times I plus the partial derivative with respect to y evaluated at that point times j. And so it would point out of the surface something like that, and down below is a projection of that vector. I made it bigger than it really is so you could see it. Note that the gradient is parallel to the xy plane, okay? Because it's two-dimensional. It's got an I and a j component, but no k component. So let's look at gradient vectors in 2D, although this is not very useful. It is, to work problems, it is a building block for 3 dimensions. So let's just take a look at a single variable function from good old single variable calculus. And so there's only one independent variable, and at the point 2, 3 then, the gradient vector is just the partial derivative with respect to x, which is in fact the derivative, as you learned it, which would be a half x, and so we have one component, and so we get always in 2D, we always get some number times I, obviously, because we've only got the first component. So it would look something like that. Now what does this mean? Well, very little, but as x moves to the right along this vector, then y will go up, y will increase, right? Now if we look at a different point, a negative 2, 3, this time the gradient evaluated at negative 2, 3 will be a half times negative 2 or negative 1, which is negative I. And so it looks something like that. As x moves to the left, this time y increases. And so the gradient points in the direction that will make y increase. Okay? Note that the gradient is always parallel, in this case, to the x-axis. So it's parallel to the x-axis in 2D, and in 3D, as we saw previously, and as we're going to look at again, in 3D, the gradient is always parallel to the xy plane, because the xy plane is the domain of our function in 2 variables, whereas the x-axis is the domain for our function in 1 variable. Note also that the gradient points in the direction x must move in order for y to increase. Okay, so we're going to build on that in the next slide. Okay, so now let's move up to the next dimension, 3D, which is where gradients start becoming useful. Here's that surface we looked at earlier. Note that these gradient vectors all point outward. These are the directions x and y must move in order for z to increase the most rapidly. Now, also note that these vectors are drawn on the xy plane, whereas what you would do, you would lift them straight up, attach them to a point on the surface, and then that would tell you which way you should move in order to ascend, go up this surface the most rapidly. So, I mean, if you're on a point here, unlike 2 dimensions, you've got several choices on how to move upward, you know, at different angles. And so if you want to move up as quickly as possible, then you use the gradient vector to point your way. Now here's another example. This time it's an upside down bowl, and notice that all the gradients are pointing inward. The gradient vectors in this example are pointing inward. These again are the directions x and y must move this time in order for z to increase the most rapidly. So now if you wanted to go downhill, what would you do? Well, you'd go in the opposite direction, and that would get you downhill the most rapidly. Now, if you change the direction a little bit, z will still increase, but not as rapidly. That is, the incline traveled will be less steep if you don't follow the gradient vector's direction. Gradient vectors can be considered in any dimension. So if you're given vector x, which is just a way of describing that you have n dimensions, and a function on those n variables in n dimensions, then we define the gradient vector of the function of these several variables, n variables, to be the vector whose components are the partial derivatives of the n variables. So you can use this in any dimension you wish. This course will focus mainly on 3 dimensions, okay? For example, if we have a function of 2 variables, z equals some function of x and y, which would be a surface in 3 dimensions, then the gradient is simply the partial derivative with respect to x for the first component and the partial derivative with respect to y for the second component, and there you have the 2 different notations we've been using. But if you're in 4 dimensions, where w is a function of x, y, and z, then you get a vector with 3 partial derivatives, and so on and so forth. 5 dimensions, 6 dimensions, however many you need. Now, the gradient vector points in the direction for which f, the function, increases most rapidly. Now, the length of the gradient vector is called the rate of increase, or the directional derivative of f in that direction. And so the directional derivative is numerical, whereas the gradient is a vector, but they are related, obviously. Gradient vectors and level curves in 3 dimensions. Okay, so we're going to go back to 3 dimensions and continue our study of the gradient. So the partial derivative of z with respect to x is the rate of change in z parallel to the x-axis, in other words, in the direction of the I vector. And the partial derivative of z with respect to y is the rate of change in z parallel to the y-axis, that is, in the direction of j. Here's an example. The gradient of z is the partial derivative of z with respect to x for the first component, partial derivative of z with respect to y for the second component, which in this case are 2x and 2y respectively. So here are some level curves for this surface. They're circles. When z is 1, you have a circle with radius 1. When z is 9, you get a circle with radius 3, and so on and so forth. Okay? All right, so at the point 3, 4, 25, I picked some nice numbers, you would get 2 times 3 for the first component, 2 times 4 for the second component. So the gradient would be 6, 8, which looks something like that. And at, say, 2.5, 0 for y, then you get the gradient 5, 0, which looks something like that. So I've attached them to the level curves, which is how they would look when you project them down onto the xy plane. And maybe you notice something. Now, I couldn't find this particular function, but here's a similar one where the level curves are showing, if you imagine those coming up towards you, you'd have the 3-dimensional surface. So this isn't the same as the one I've shown there, but it's similar. And so it kind of gives you an idea of what happens as the level curves move up the surface. There are some gradient vectors drawn for you, and you should be noticing something interesting. And that is that the gradient is always perpendicular to the level curves of z. That's a very useful fact. Here's what the z equal x squared plus y squared might kind of look like. It's a paraboloid. Now, why is this true? Why in the world are, I mean, these are derivatives, right? I mean, you would think you'd get some kind of tangent, not a perpendicular, so that's kind of weird. So, for example, let's say we have y equal x squared as a level curve. Okay, so this is a level curve. And if you are standing on a level curve and want to walk some small distance to get as far as possible from the level curve, you want to walk along the normal, right? Otherwise, if you move in any other direction, you're not going to get away from the curve nearly as quickly. And remember that the gradient points in the direction of greatest increase. So there goes Mario, normal to the level curve. In this case, f of xy would be x squared minus y. That's how you would determine the z value. Looking at y equal x squared and just moving the y to the other side. And so the gradient is 2x comma negative 1. And that vector looks something like that. At that particular point, x is 2. So Mario would move 4 units to the right and down 1. It's a little bit off, but you get the idea. Okay, so to revamp just a little bit, here's an interesting surface. The gradient vector, again, of the function z describing the surface would be the partial derivative with respect to x, comma, partial derivative with respect to y, and then at a particular point, you would evaluate those and get a numerical vector. All right, so let's say this is a point, and there's the gradient, let's say. Then if x and y move in the direction of the gradient of p, of that point p, z will increase more rapidly than if x and y move in any other direction. Okay? Now, the length of the gradient vector is called the maximum directional derivative or maximum rate of change in z per unit moved in the xy plane. This is, if you follow this vector, you get the maximum change in z. You follow any other vector parallel to the xy plane and you will get less of a change, a smaller change in z per unit. Okay, now we're going to move up to gradient vectors in 4D. So this time we have a rate of change with respect to x parallel to the x-axis in the direction of I. We have a partial derivative that gives you the rate of change in w parallel to the y-axis, in other words, in the direction of j. And then the partial derivative with respect to z, this time will give you the rate of change in w with respect to the z-axis, in other words, in the direction of k. So now we're adding to our vector, instead of a two-dimensional vector parallel to the xy plane, we're going to get a three-dimensional vector. Now, remember that when we had a function of two variables, the gradient was perpendicular to the level curves, right? So what will this vector be perpendicular to? It will be perpendicular to the level surfaces of W. Well, how is that useful? Well, for example, if we have this four-dimensional object which we cannot draw, it will, however, have a set of level surfaces. And so if we take its gradient, it will be perpendicular to any level surface. And a level surface is described by changing W to a constant. And there we have a surface in 3D. And if we use the three-dimensional gradient, then we get a vector perpendicular to the surface. And it will be a norm then to the surface, and therefore a norm to the plane tangent to the surface at a particular point of choice. So that's going to be very useful. Okay, so here's a couple of surfaces that maybe could be level surfaces for some function w in x, y, and z. And let's look at the yellow one, which has gradient vectors poking out of it. And these are three-dimensional gradient vectors, so they're not parallel to the xy plane. And notice that they are all perpendicular to that yellow surface. So this time we still have a surface, and maybe it can be described by z equal a function explicitly in a function of x and y, or maybe it's given to us implicitly. It doesn't matter because we don't have to solve for z, we're just going to need the three partial derivatives. However, to get vectors perpendicular to the surface rather than to the level curves, we need to think of this as a level surface. one of many where w equals a function of x, y, and z, which in this case, if we're given z explicitly, then the g function is just going to be acquired by moving z to the other side and getting f of x, y minus z. So perhaps this yellow surface is a level curve where w is 0. Maybe it's some other number, but when we compute the gradient, we don't care about that other number, because when we take the partial derivatives, whatever number is on the left there will go to 0. So the gradient then is just going to be the vector whose components are the partial derivatives with respect to x, y, and z respectively. Gradient vector applications. So let's say we have a surface, the blue surface, and maybe we have a curve on the surface described parametrically from previous lessons. Then you're going to have a vector tangent to the curve and therefore tangent to the surface at a particular point. And we've learned how to do that in the past. But now if we have a three-dimensional gradient at that point, it will be perpendicular to the curve and to the surface. The gradient g is normal to the surface of g of x, y, z equals c, where that's your blue surface right there. Now the gradient is normal, so we can call it n, and there's some more notation for our gradient. And so let's call it the normal to the surface. And if we have a tangent plane to the surface, then our gradient is also normal or perpendicular to that tangent plane. And so let's say we have a point x, y, and z on that plane. Then we can have a vector on the plane, and that vector will be using head minus tail, using the generic point x, y, z, and the particular point at p0, x0, y0, z0, we get this vector on the plane. Now, hopefully you remember that if we dot the vector on the plane with its normal, we get 0, because two vectors that are perpendicular dot to 0. And so by doing this, we can get an equation for the tangent plane. And multiplying that out, we get the partial derivative with respect to x at the point times x minus x0 plus the partial derivative of y at the point times y minus y0 plus the partial derivative of z at the point times z minus z0 equals 0. And then you can simplify that when you have actual numbers, and we'll look at some examples here in a minute, and get a nice equation of a tangent plane. So this is another application. This is an application of the three-dimensional gradient vector in order to get an equation of a tangent plane. Another application is when you have two surfaces. So we've got a green surface and a blue surface, and they intersect at that red curve. Let C be the curve that is the intersection of two surfaces, G and F. Well, the gradient for G is perpendicular to the green surface, and the gradient for F is perpendicular to the blue surface. Both gradient vectors are perpendicular to their respective surfaces, and therefore both are perpendicular to C. So if you have an intersection curve and you're trying to find an equation for it, what do? Well, if you cross F, the gradient of F with the gradient of G, then you get a vector perpendicular to both of them. And so if it's perpendicular to both of the vectors perpendicular to C, then it has to be the tangent vector to C. And so now you have a way of finding a tangent vector to a curve of intersection. Now we're going to look at directional derivatives. In mathematics, according to Wikipedia, the directional derivative of a multivariate differentiable function along a given unit vector, u, at a given point p0, given by whatever the n variables are in n-dimensional space, represents the instantaneous rate of change of the function moving through p0 with a velocity specified by the vector u. Now see, in this case we're generalizing. Vector u does not have to be the gradient vector. If u is the gradient vector, then you're going to get the maximum directional derivative value. Okay? But you could move along a different vector. in which case you get a different directional derivative, a different velocity in movement of the function. So here's the formula, and we're not going to prove why this works. If you want to move along a different gradient, then the directional derivative will be the dot product of the gradient vector with the vector you want to move along with respect to the n variables. Now, if you're moving along the gradient, then you just dot it with itself, which gives you its length. Okay? Note that if we take the directional derivative along the I vector, we do in fact get our partial derivative with respect to x back, which makes sense. And if we take the directional derivative in the direction of j, then we get our partial derivative with respect to y back, and so on. And so the definition makes a lot of sense when you take a look at the different components. Now, if you change the u to have several components, then of course that adjusts the rate of change accordingly. Directional derivatives continued. Given vector v of several variables, n variables, and x, which is your actual variables in your function, same number of variables, then if u equals the unit vector in the direction of v, the directional derivative of f at the point p0, which you have specific values for your n variables, in the direction of u is given by this limit. And so if you want to develop the formula, you can feel free to do that. But we're just going to use the directional derivative dotted with u because that's what it comes out to be. So circle that formula. That's what we're going to use. So we can compute the rate of change in z when any vector parallel to the xy plane is followed. However, the greatest rate of change in z will occur when we move in the direction of the gradient vector, namely the two-dimensional vector fx, fy, normal to the level curve. That will, if we move normal to the level curve, that will push us away as quickly as possible, and z will increase most rapidly. And then if you go in the opposite direction, you're going to have the greatest decrease in z. So number 4 says to compute the gradient vector at the point 3, -1, given f of x, y equals this value. Now they didn't give the z value at that point, and that's okay because we don't need it. So we have to compute the partial derivatives for x and y, and I won't belabor that. You already know how to do that. There's the partial derivative with respect to x, and then with respect to y. Notice the only thing different is applying the chain rule. We get a different tag there. And then, of course, we throw in the values 3 and -1 for x and y. So there's our gradient vector. That's all they asked for. Number 8, compute the gradient vector at the point 2, 1, 0. And again, notice they don't give you the w value because you don't need it. You could, you just don't need it. So this time we need 3 partial derivatives, and these are easy. And after we compute the partial derivative, we put in the values for x, y, or z as needed. So there's the partial derivative with respect to y. Partial derivative with respect to z is a little bit more complicated, not much. And so our gradient vector at that point is just 4, 0, -3. Number 12, compute the directional derivative where the vector u is the unit vector in the direction of v, given this function, this point, and this vector. So we're going to use this formula. So we need to compute vector u, the unit vector in the direction of v, and we need to compute the gradient vector, after which we do the partial derivatives. We have to plug in the values given for x and y for the point p 0, pi over 4. And then we dot those two vectors to get our directional derivative. And notice the directional derivative is always a number. This means that there would be no change in z along that particular vector, if x and y moved along that particular vector. Number 18, compute the directional derivative d sub u f of p, where the vector u equals the velocity vector divided by its length, if the function of x, y, and z is equal to log of 1 plus x squared plus y squared minus c squared. The point in question is 1 comma negative 1, 1, and the velocity vector, the direction in which we're going to compute this derivative, is the vector 2, negative 2, 3. So here's our formula. We need the gradient of f dotted with u. So let's figure out what u is by dividing v by its length. And there we have a lovely vector of u. Now the gradient, which is fx, fy, fz, each of which is 1 over the quantity inside the logarithm, and then times the partial derivative of x, which is 2x, partial derivative of y, which is 2y, and the partial derivative of minus 2z squared, which is negative 2z. Lovely. But now we have to plug in the point, because we're getting a numerical answer here. So I plugged in 1 for x, negative 1 for y, and positive 1 for z. And we get a nice looking gradient vector, 1 comma negative 1 comma negative 1. Doesn't get much better than that, eh? So now all we have to do is dot those two vectors together, u dotted with the gradient in either order. And so we get 1 times 2 over root 17 plus 2 over root 17 minus 3 over root 17, which equals 1 over root 17. And that is the directional derivative. Remember, the directional derivative is always a number. And also remember that the maximum directional derivative will be in the direction of the gradient, not in the direction of any other miscellaneous velocity vector, such as in this problem. Number 22, compute the maximum directional derivative of f at this point given this function. Well, now recall that the maximum rate of change is along the gradient. So the gradient is a directional derivative, specifically in the direction of greatest change. So what they're really asking for is the length of the gradient vector. Maximum directional derivative equals the magnitude of the gradient. So we have two partial derivatives, and we have to use the derivative of arctangent, which is 1 over 1 plus whatever the quantity inside is squared. And then because the quantity inside the arctangent was a quotient, we need a derivative of the inside using the quotient rule. And notice that the first time the derivative of y is 0 and the derivative of x is 1, whereas when we do the partial derivative with respect to y, the derivative of y is 1 and the derivative of x is 0. So simplifying that, we get these two expressions, which we then plug in 2 and negative 3 for x and y respectively, and there is our gradient vector at that particular point. The maximum directional derivative is the length of the gradient vector, so we plug that into our length formula or magnitude formula, and we get square root of 13 divided by 13. The maximum directional derivative is square root of 13 divided by 13. Notice that directional derivatives are numerical. Number 30. Use the normal gradient vector to write an equation of the line tangent to the given curve, 2x squared plus 3y squared equals 35 at this particular point. Alright, so here's a picture of the ellipse represented by this function. It's only in two variables there, so it's not a surface. And the gradient vector is perpendicular at the point 2, 3 to the tangent line and to the ellipse then. And the gradient vector has two components. This is like a level curve, you see. And the two components are 4x and 6y, which when we plug in our 2 and our 3, we get 8, 18. And the gradient vector acts as a norm to this level curve. And so there's our tangent vector, by the way. Our tangent vector is just, now see, we're doing this as though it were a plane. We're using the same formulas and method as we did when we were finding the equation of a plane. So we're just pretending it's a plane, but only with two two components, and so a plane with two components is a line. And so then we dot n and t. This is pretty cool. And we set that equal to 0, because if we dot those two perpendicular vectors, we get 0, and then we simplify, and we get the equation of a line. Pretty cool, huh? So we're using our three-dimensional method to do a two-dimensional problem. Now, we didn't need to do that. You could have easily done this last year in single variable calculus using the tools you had then. But this is just to show you that our new tools work on every level. Haha, every level, get it? I kill myself. So now let's do it in where we're used to using this method. Use the normal gradient vector to write an equation of the plane tangent to the given surface, which has an x, y, and a z in it at this particular point. So the method's the same. This time we will get a plane. So here's a picture of, I don't know what the surface really looks like, but we'll just pretend it's some curvy surface, and then the green plane is tangent at that point, and the gradient vector is perpendicular, and so the gradient vector can be used as a normal to the plane tangent to the surface. So we need the gradient vector, so we compute the partial derivatives, which by now you're expert at computing. Then we plug in the particular values at that point, and we're going to use that gradient vector then as the normal to the plane. And then if we want a generic vector on the surface of the plane, it will be x minus 5, comma y plus 2, comma z minus 3, using a generic point x, y, z and the given point. So then all we have to do is dot n with v, because that will be 0 if they're perpendicular. Multiply it out and simplify. Okay, one more example. Use the normal gradient vector to write an equation of the plane tangent to the surface defined by f of xy equal x divided by y at this particular point. So we need to consider this as a level surface. So f of xy can be considered a third variable z, and then we just move z to the other side, and that is a level surface for the function of three variables, namely w equals g of x, y, z equal what we have there, x over y minus z, where w is 0 for this particular level surface. Hence, the gradient vector, gradient g, will be perpendicular to the surface of the given two-variable function x over y. So we need the partial derivative with respect to x, which necessitates the quotient rule. So we have the denominator y times the derivative of the numerator, which is 1 if x is your variable, minus the numerator times the derivative of the denominator, and the derivative of y with respect to x is 0, and that's all over the denominator squared, y squared, and then z just goes to 0 because we're considering x as our independent variable. Then the partial derivative with respect to y, again we use the quotient rule, but this time we have the denominator y times the derivative of the numerator, and this time y is our independent variable, so x is considered a constant, goes to 0, minus the numerator times the derivative of the denominator, which with respect to y is 1, again over y squared, and again z goes to 0, and that simplifies to negative x over y squared. And finally, the partial derivative with respect to z is just negative 1 in this case. So at this particular point, we get our normal vector, which is the gradient vector g evaluated at p. And so we just put in 6 for x, 2 for y. So for the partial derivative with respect to x, we get 1 over 2. For the partial derivative with respect to y, we get negative x, which is negative 6 over 2 squared. Negative 6 over 4 reduces to negative 3 halves. And then, of course, our partial derivative with respect to z is just negative 1 at any point. Now, we dot n with any generic vector on the tangent plane. So it's just x minus 6, y minus 2, z minus 3 for the vector on the tangent plane. And continuing with the dot product, we set that equal to 0, and then we can simplify that a little bit, which I didn't show all the steps, but you can do the algebra. And there we have a very nice equation of the plane tangent to the surface, f of xy equal x over y at the point 6, 2, 3. Now let's review a little bit, because in previous years students have had issues with these different kinds of gradients in the different dimensions. So I just want to go over a few things again. Now, given z equal f of x and y, a function of two variables, the gradient vector is given by the partial derivative of x and the partial derivative of y, and it will be parallel to the xy plane and perpendicular to level curves c equal f of x and y. So in other words, if you replace z with a constant, then you have two variables, x and y, and you can graph it on the plane. And if you graph the gradient vector, which is already parallel to the xy plane, on the xy plane, all those gradient vectors will be perpendicular to the level curves. Note that z equal f of x comma y is a surface in 3 space. Okay, and so the gradient vectors to that surface are perpendicular to the level curves. Okay, so for example, let's say z is equal to x squared plus y squared. Then the gradient vector would be 2x comma 2y. And if we take a look at 4 points on the surface, z equal x squared plus y squared, that's why they have 3 components. These are points on the surface. And then we can compute the gradient at each of these points. And notice that the lengths are also computed there for you. And here's a picture of those gradient vectors attached to the surface. The one that's the red one that looks like it's pointing down is actually still parallel to the xy plane. The way it's drawn is for perspective. Okay, so all of these vectors are parallel to the xy plane. Now let's take a look at a picture of the same gradient vectors, but only looking at the level curve. So now we've put them all down on the xy plane, and those are the 2 circles that were shown in the previous picture, except they are now reflected down onto the xy plane. And so you can see that all 4 of these gradient vectors are perpendicular to the level curves. Now let's go up 1 dimension. Put on your thinking caps. Recall that the 2-dimensional gradients, f sub x comma f sub y, are perpendicular to level curves of a 3D surface. Now, 3D gradients will be perpendicular to level surfaces derived from a 4-dimensional function. W, let's say, equals a function in x, y, and z. Because it's the same kind of relationship, you're just going up a level. So instead of perpendicular to level curves, the 3D gradients are perpendicular to level surfaces. And this leads into a very clever trick concerning just looking at the 3-dimensional surface, which is what we're going to talk about next. So let's continue our review. This time we're going to be given a function of 3 variables. So you really have 4 variables. W is the dependent variable, and x, y, and z are all independent variables. And then the gradient vector then has the 3 partial derivatives of w, one with respect to x, then y, and then finally the third one is the partial derivative with respect to z. This gradient vector will be perpendicular to any level surfaces where you replace w with a constant. Now, as soon as you replace w with a constant, you have a 3-dimensional surface, right? So this 3-dimensional gradient vector will be perpendicular to the surface. Now they're no longer parallel to the xy plane. For example, let's say z is a function of 2 variables, and so it's a surface. We can view it as a level surface. Now, how's that? Well, how do we find w, a function of 3 variables, that relates to this surface? Well, what we do is we simply subtract z from both sides, and now we have a level surface for a function in 3 variables where the w value is 0. And so w is just x squared plus y squared minus z. So we call w a function. Now, the reason we're changing it to g is because we already have a function f in this example, which is the function of 2 variables. So we can't really call a function of 3 variables, even though it's related by the same letter. So we're going to call it g. W equals g of x, y, and z equals x squared plus y squared minus z. And so the original surface is the level surface of this four-dimensional function when w is 0. Alrighty, so there's the gradient vector then, taking the partial derivatives of g with respect to x and then y and then z. And notice that the partial derivative for z is -1, and it'll always be that way if z is stated explicitly as a function in x and y. In other words, z equals, and then your x and y terms are always on the right side of the equation. Now let's look at gradient g at the same 4 points as before, because this is the same function we looked at before when we examined the level curves and the two-dimensional gradient vector. So let's move that up. And we're going to compute the 3D gradient vector at each of the same 4 points that we looked at for the two-dimensional gradient vector. Notice they're a little bit longer. And then let's move those down so we can take a look at a picture. So there's the same surface, but this time we have 3D gradient vectors that are perpendicular to the surface. Now they're a little bit harder to draw, so I left in the little dotted lines that help guide my drawing. And you have to use a little bit of imagination. Those are all perpendicular to the surface. They are not parallel to the xy plane. So that's the difference. We're treating these three-dimensional gradients to the surface as though the surface was a level surface for a bigger function in 4 dimensions. And of course we can't draw the 4-dimensional function, so don't worry about that. Now another thing to note is that if we want the equation of a plane tangent to the surface at point P, then we can use the gradient vector at point P as the normal, because if it's perpendicular to the surface it'll be perpendicular to the tangent plane. And then all we have to do is dot that gradient vector with a vector on the tangent plane, which we get by taking x, y, and z and subtracting the point values at P. Okay, one more comment just to clarify something else that was a point of confusion in past years. If z is given implicitly, then the gradient vector perpendicular to the surface is still the partial derivatives, and it can be derived similarly to when z is given explicitly. What do I mean by implicitly given? Well, for example, let the surface be described by z squared plus 4y squared minus 2x equals 3. Then w is a function of x, y, and z, and our surface is just the level surface for when w is equal to 3, you see. So implicitly means that z is all mixed up with the other variables, and so it's not described, it's not solved for. In other words, you don't have z equal an expression in x and y, it's all mixed up. But you can still, it's in fact it's even easier to compute the gradient vector, which in this case would be -2 for the partial derivative with respect to x, 8y for the partial derivative with respect to y, and 2z for the partial derivative with respect to z. And so in this case, you may not end up with -1 in that third spot. But if z is given explicitly and it's all by itself on the left, then when you bring it over, it's always going to be minus z, and that third partial derivative is always going to be -1. So that's the difference between the way z is given to you, or the way the surface is described. Now note that whenever z is given explicitly as z equals f of x comma y, which is what I just said, the partial derivative with respect to z will always be -1, because, like I said, we're bringing z over to the other side. But if the function in 3 variables with z is all mixed up with the x and y, then that's said to be given implicitly, and that third component will probably not be -1. Okay, so I hope that clarifies some things for you. And so now I leave you with a beautiful picture of a shimmering surface to do the problems on your own. Enjoy!